Hey, and welcome to my next video on discrete calculus, where we'll explore a couple of basic forward difference formulas. Before we begin, I'll just give a quick disclaimer about the prereqs. I try to make my videos as accessible as possible, but sometimes some prior knowledge is important to understand the concepts we talk about. This time, the math here isn't that hard. I'd suggest watching my last two videos because we're going to mention some of the same sequences we already talked about, but other than that, I'd recommend knowing some formulas for E, and that's it. So let's get to it. Okay, so the first thing I want to do is talk about the discrete analog of E. So what is E in the first place? Well, you probably already know since I just told you that you should, but one way of defining it is that it's the unique number satisfying this property. The derivative of e to the x is itself. The discrete analog of E is the unique number r satisfying the same property with the forward difference operator instead of the derivative. Now, we actually already talked about how you can solve this. So we'll set the forward difference of some sequence equal to itself, and then we'll expand out the definition of the forward difference operator. Then we'll add a of n to both sides, and we end up with a of n plus 1 is equal to 2 times a of n. And we already talked about how to solve this recurrence. The solution is a of n is equal to 2 to the n times a of 0. This means that some constant times 2 to the n is the unique sequence whose forward difference is itself. So it's not all that magical, but the discrete analog of E is 2. We probably could have figured that out just by thinking about it, really. If the difference between the next term and the current term is the current term, then the next term is twice the current term, which is basically the definition of 2 to the n. We can also solve for a sequence whose forward difference is any constant multiple of itself. So we'll set the forward difference of some sequence equal to c times itself, expand out the definition of the forward difference operator, add a of n to both sides, and then we can compose this relationship k times to get the formula for adding inputs. Then we set n equal to 0, and then with a simple change of variable, we will find our sequence. So it's clear that the sequence a of n is an exponential with base c plus 1 multiplied by a constant a of 0. Now our c was the constant of proportionality between the forward difference and the sequence. If we set c equals 1 like we would with the case of the E analog, we can see that the base of the exponent becomes 1 plus 1 equals 2. It also turns out that if you use smaller and smaller step sizes for the forward difference, the E analog converges to the regular E. Let me show you. First, we'll find the forward difference of an exponential of base r in any particular subscript. So this is just the definition of the forward difference. Now we can factor out an r to the n from both of these terms. And note that this big thing out front, r to the h minus 1 all over h, is a constant, at least in respect to n. Also note that you can set h equal to 1 to receive the formula for the unsubscripted forward difference operator. This isn't that surprising coming from the c plus 1 to the n that we just found. In order to find the r that is the analog of E for a specific base, we need to set that multiplier, r to the h minus 1 over h, to 1 and solve for r. So we'll multiply both sides by h, add 1 to both sides, and then take everything to the power 1 over h. Now that might look familiar. The limit of this expression as h goes to 0 from the right is E. If that doesn't look exactly like the expression for E you've seen before, that's a quick fix. So let's try evaluating the limit. So we'll do a quick change of variable with h equals 1 over x. And now the limit as 1 over x goes to 0 from the right is the limit as x goes to infinity. And this should be the definition of E that you were presented with in the context of continuously compounding interest, for example. So the limit of r as h approaches 0 from the right is E. Before we move on from the exponential sequence, I want to take the forward difference of 2 to the n directly because I haven't done that yet. So this is just the definition of the forward difference. And then we'll pull out a factor of 2, and then we'll combine like terms, and we get 2 to the n just like we'd expect. Now that we have an analog for the exponent rule, we might as well search for an analog to the powers of x rule. The forward difference of a power of n isn't exactly what we're solving for. This isn't actually that bad, but it isn't pretty. Instead, we're looking for a set of sequences with properties analogous to the powers of x, but in discrete calculus. In calculus, the powers of x are special because of the following property. The derivative of x to the n is equal to n times x to the n minus 1. So what we're looking for is some sequence of sequences that follows the same property but with the forward difference instead of the derivative. Starting with n equals 0, we can actually go ahead and solve for the first few of these. So delta a0 of x is equal to 0 times a minus 1 of x, which is of course 0. So we can sum both sides from k equals 0 to x minus 1, and then the right-hand side becomes 0. And then we can apply the fundamental theorem of discrete calculus, and then add a0 of 0 to both sides. So it seems that the first sequence here is a constant sequence. All the terms in the sequence are equal to the first term. Since the forward difference is linear, any constant multiple times the sequence of sequences we're looking for still satisfies the same forward difference property. And since the forward difference of a constant is 0, we can also add any constant to any term of our sequence and it still retains the desired property. As such, we can feel free to pick any starting value we want for any of the sequences in our sequence of sequences. There are a lot of possible sequences that follow this property. To mirror the powers of x as closely as possible, let's just say that the value of the sequence at 0 should be the same as the corresponding power of x at 0. In the case of x to the 0, we get 1. Now, I know what you're saying, 0 to 0 isn't 1. But if we're treating the powers of x as a sequence of analytic functions, as we should, f of x equals x to the 0 at 0 should be equal to its limit, which exists and is 1. Anyway, we would conclude that a0 of 0 is equal to 1, and therefore a0 of x is equal to 1. This is the first sequence in our sequence of sequences. From here, we can find the next sequence. So delta a1 of x is equal to 1 times a0 of x, which is of course just 1. Then we can sum both sides from k equals 0 to x minus 1. And now the right-hand side represents adding 1 to itself x times, which is just x. Then we can apply the fundamental theorem of discrete calculus yet again. And just like before, we're forced to pick the first term in our sequence. Again, we'll just say that it's the same as the corresponding term from the powers of x, which in this case and in all cases going forward is 0. So a0 of x is 1 and a1 of x is x. So now we have the second sequence in our sequence of sequences. Let's find another, remembering that a2 of 0 will also be 0. So delta a2 of x is equal to 2 times a1 of x. So we can plug in our expression for a1 of x as x. And so now we can sum both sides from k equals 0 to x minus 1. Then we'll pull out this 2. And now we already know how to evaluate this sum because we did so in the last video. So we'll go ahead and apply that formula. Then the 2's will cancel out. Then we can apply the fundamental theorem of discrete calculus yet again. And now a2 of 0 will be 0. And so a2 of x becomes x times x minus 1. So now we have our third sequence. That was easy enough. You might be noticing a pattern, but because it isn't super obvious with just 3 sequences, we're going to derive one more term. So far, it's been a walk in the park, but the next one ends up being much, much harder. I could just tell you what the pattern is, but we're going to derive one more sequence because it will let us practice what we learned in the last video. So delta a3 of x is equal to 3 times a2 of x. So again, we'll plug in our expression for a2 of x. Then we'll sum both sides from k equals 0 to x minus 1. Then we'll pull out this factor of 3. Then we'll apply the fundamental theorem of discrete calculus yet again. Then a3 of 0 will be 0. And so we're left with this expression for a3. So we need to evaluate this sum, which actually totally sucks. So let's isolate it for just a second. So first we can multiply out this k, and then split apart the sum. We know how to evaluate the second sum because we already did. I don't really want to evaluate the first sum, especially because some people know the formula, but screw it, we're going to do the first sum with the same technique we did for the second sum in the last video. I know there are way better ways to do this, but I want to demonstrate that we can evaluate the sum without being clever at all. So we'll set s of x equal to the sum from k equals 0 to x minus 1 of k squared. Then we'll take the forward difference of both sides. Now every term is going to cancel out except that x term at the top, and so we'll get that delta s of x is equal to x squared. We could take the forward difference a bunch more times if we wanted to, but the n plus 1th forward difference of an nth order polynomial is 0. So if we just take the forward difference another 3 times, we'll get 0, just like I talked about in my first video on discrete calculus. So the fourth forward difference of s of x is equal to 0. At this point, because I respect my well-being, we're going to use the formula for the third difference that we found in the last video. So then we'll expand out the fourth difference in terms of the third difference, and then apply this formula. So we'll distribute across this negative, and then like terms are going to appear on the diagonal. So we'll end up with 1 of the x plus 4 term, minus 4 of the x plus 3 term, 6 of the x plus 2 term, minus 4 of the x plus 1 term, and 1 of the x term. So now we have a decent-ish recurrence relation. We can then solve for the roots of the characteristic polynomial. So r to the fourth minus 4r cubed plus 6r squared minus 4r plus 1 is equal to 0. So this factors out into r minus 1 to the fourth. So r is equal to 1 or 1 or 1 or 1. Yep, as you probably guessed, there was going to be a bunch of repeated 1s for the roots. In fact, that's the case for every polynomial, and we probably could have guessed that our sum would be a polynomial. But whatever, we're here, and now we're going to write the general form of our solution. So let's look back at our initial sum to get 4 initial conditions. So we'll plug in 0, 1, 2, and 3. Now, if you're uncomfortable with the bounds of the first sum, we should note that it should be the empty sum, 0. There are n plus 1 integers between 0 and n, so there should be 0 integers between 0 and minus 1. While the sum from k equals 0 to 0 will have one term, this sum will have no terms. So we can then evaluate these sums as 0, 0 squared plus 1 squared, and 0 squared plus 1 squared plus 2 squared, which is 0, 0, 1, and 5. Then we can plug in our general solution to these evaluations. So now we can multiply out these terms. Now, we could solve this system by hand if we wanted to, but at this point, we're just going to rewrite the system as a matrix and give it to Wolfram. So we'll factor out this C vector, and then we'll type this whole thing into Wolfram. So we get 0, 1/6, 1/2, and 1/3. So therefore we can write our sequence as follows, which of course becomes s of x is equal to 1/6 x plus 1/2 x squared plus 1/3 x cubed. And this is the value of our sum. Now we can factor out an x and get a common denominator to make our expression a little bit easier to use. So the first term is going to contribute a 1, the second term is going to contribute a minus 3x, and the third term will contribute a 2x squared. So now we should recall why we're actually doing this, the powers of x analog. So we had that a3 of x is equal to 3 times the sum from k equals 0 to x minus 1 of k times k minus 1. So we'll split apart the sum, and now we have a formula for each of these two sums. So we can go ahead and plug those in. Now, just so we can combine terms, we're going to get a common denominator and then factor a negative into the final term there. Then we can add like terms. And now the 3 is going to cancel with the 6 to get a 2. Now we can pull a 2 out of the parentheses there. And then the 2 will cancel out as well. Now this quadratic will factor into x minus 1 and x minus 2. So we get that a3 of x is equal to x times x minus 1 times x minus 2. Now you might be able to guess what's going on here. There appears to be a recurrence relation to the sequences. It looks like a n plus 1 of x is equal to x minus n times a n of x. Let me remind you of the property that we're searching for. We can use induction and the discrete product rule to show that our hypothetical recurrence relation for our sequences satisfies the desired property. So we'll use this forward difference property as our inductive hypothesis, and then we'll use the statement at the top as the definition of our sequence. Then we'll show that the next inductive hypothesis holds. So delta of a n plus 1 of x is equal to this by the definition of a n plus 1 of x. Now we can expand this using the discrete product rule that I derived in my first video on discrete calculus. So then we'll pull a negative out of the 1 minus n term and expand delta a of n with the inductive hypothesis. Then we'll reorder these factors. And then we'll note that x minus n minus 1 times a n minus 1 of x is equal to a n of x from the definition. Now we can expand out the forward difference of x minus n, and everything except the 1 will cancel out. Then we can combine like terms, and we get that delta a n plus 1 of x is equal to n plus 1 times a n of x, which is the next inductive hypothesis. So then by induction, we can conclude that the forward difference property applies to every term in our sequence of sequences. So looking back at the definition for our sequence of sequences, we can compose it k times to get the formula for adding inputs, and then as usual, we set n equal to 0. Now we should note that the first term in our sequence of sequences, a0 of x, is equal to 1. So then with a simple change of variable, we'll end up with an expression for a n of x. This sequence of sequences is called the falling factorial for its similarity to the conventional definition of the factorial function. In fact, this function can be extended to non-integers using the factorial, or really its analytic continuation, gamma. You can check that out on the Wikipedia page, which I've linked in the description if you're curious. Beyond having a fancy name, this function also has its own notation. Well, it has too much of its own notation. One such notation is called the Pochhammer symbol, introduced by Leo Pochhammer and written as shown. However, some authors also use this notation to denote the rising factorial, which is defined similarly to the falling factorial, except with a plus k instead of a minus k in the product. Pochhammer himself also apparently used the Pochhammer symbol to denote the plain old binomial coefficient. Because it would be confusing to use the same notation for the rising and falling factorial, some authors have switched to using this notation to denote the rising factorial. But I don't like that either, since it looks like the notation for the nth derivative. Some authors agree, and so different notation has also been created, such as x super underbar n for the falling factorial and x super overbar n for the rising factorial. That's decent, but although it's unlikely that complex exponentiation and the rising factorial would appear in the same context, the overbar still looks like the notation for the complex conjugate of n. As such, to be as clear as possible, I've decided to use a hybrid approach. So double parentheses around the x, and then underbar parenthesis, underbar parenthesis, underbar parenthesis, underbar parenthesis around the subscript of n. This method is as clear as possible and will not be confused with anything else. JK, that'd be stupid. I'm going to use the Pockhammer symbol. So bam, that took a while, but this sequence of sequences is the discrete analog of the powers of x in the sense that it obeys this property. The forward difference of the nth falling factorial of x is equal to n times the n minus 1th falling factorial of x. Now you might be wondering if it was worth going through all this effort to come up with a pretty random property of a pretty random sequence of sequences that we just made up. And it is. No spoilers, but it allows you to create a discrete analog of the Taylor series. But that's for another video. I'll catch you then. Sequence of sequences, sequence of sequences, sequence of sequences. Gosh, that's hard to say.